Hello, everyone, and welcome to today's webinar on characterization of surface modified polymers. Our presenters for today are Daniel Sullivan, Account Executive, and Yannicka Schneider, Senior Scientist and Project Manager. My name is Rena Samsu, Marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You'll have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. Jennifer Hoffman, one of our managers at EAG, will be answering some of the questions during the presentation, and we'll also collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce our first presenter, Daniel Sullivan, Account Executive at EAG Laboratories.
Hello, everyone. Thank you for attending today. Yannicka and I and a couple of other people at EAG were working on this for the last year or so, and COVID has made it all very interesting. But we've written a couple of papers, and we've been able to take that information and give a webinar here about the characterization of surface modified polymers. And we'd like to go through and explain what it is we've done and get some feedback from you guys on what's helpful, what's not helpful here. First of all, this is me, that handsome gentleman there. This is a while ago, but I'm a PhD in chemistry from UC San Diego, and I got my bachelor's at Berkeley. Go Bears. I've been in industry since the 80s, and there's my contact information if you need to get a hold of me or have any questions about this presentation or anything that EAG does. Feel free to get a hold of me. I do want to introduce Yannicka, my co-speaker here. And Yannicka, if you want to come on and tell them about yourself.
Hello. Hi, everybody. Thank you so much for joining. My name is Yannicka Schneider, and I am a senior scientist and project manager. I also did a postdoc at Berkeley, and I got my PhD at UC Santa Barbara. I've been at EAG for about 8 years, and I specialize in characterization of polymer materials and manage projects that involve many different techniques, focusing on failure analysis, deformulations, and other analyses. Thank you.
Thank you, Yannicka. So our outline for today, we're basically going to tell you a little bit about EAG, and then the plasma treatment process we put the samples through to get them ready. And then the different techniques we used here, and they have different depths of analysis. We used XPS that looks about 5 to 10 nanometers, so that's very surface sensitive. Then we also used FTIR, which looks significantly deeper, approximately a micron into the material. And we did contact angle, which is sort of a bulk technique, a bulk property. We'll talk about the results and we'll go to a conclusion. So first of all, about EAG. EAG was set up in 1978. I started competing with EAG in 1986, and eventually I wound up coming home to EAG. I've been here about 6 years now. It's a great place. We have 17 different laboratories across the world. The work that we have done here has been done in the Northern California laboratory up here. We have 3 different labs, one in Milpitas, one in Santa Clara, and one in Sunnyvale. This work was done in Sunnyvale. But we do have multiple laboratories across the United States, Europe, and Asia. So we can work in any part of the world. This is our SMART chart, and I actually had to be taught what this means. It's spectroscopy and microscopy analytical resolution tools, although I've been told one of our VPs has a better name. It's called Show Me All the Right Techniques. But essentially, this bubble chart shows the technique, and on the left-hand side, it shows the detection limits for the elements you're looking at. And then on the bottom side, it shows the resolution that you can get. Recently, we have added some techniques that are outside of the actual chart that do things that aren't exactly in the chart. So things that do like AFM, doesn't detect materials, but it has a resolution. It shows you topography, for example. This is a great chart, and if you ever want a copy of this, I believe we have some posters we'll happily send out to you. I used to use this even when I competed with EAG. I used to use the mouse pad that had this on it because it was just such a great little cheat sheet for what makes sense to do on your analysis. So the sample materials we got, I was able to obtain 3 polymer samples from a very nice company that sent me some demo units. We got polypropylene, polycarbonate, and polyoxymethylene. So these 3 things are very different surface chemistry. One is simply a hydrocarbon, one has carbon bonds, carbon oxygen bonds and double bonds. The other one has some aromatics. So we use these 3 to really see how we could tell the difference of how these surfaces would react when altered by a plasma. What we did is we basically took the bars they had sent us of these polymers and we cut them down to uniform sizes, and we split them into 3 groups. So the surface group was cleaned, but no other surface preparation. The other one we exposed to an oxygen plasma, and the third set we exposed to a fluorine plasma. They were all put in at the same time. So we ran the oxygen plasma one time with all 3 different polymers in it. So they had the exact same conditions. And we repeated that for the fluorine. So this basically shows what we did. Initially, you have the as received and cleaned surface. We put it into the F2 plasma. And we expect that we'll fluorinate the surface with single bond, CF, CF2, and CF3. We don't know that, but that's what we expect to happen. So that's why we have to go do the analysis to see what actually occurs. We used an X-ray photoelectron spectroscopy tool. It's also known as ESCA, as well as XPS. It uses a monochromatic aluminum K alpha source to radiate the samples, and it detects the electrons that are ejected from the sample. It's very surface sensitive, top 10 nanometers at most. It gives you elemental composition, except for hydrogen and helium, can't see those, and it gives you some chemical information. And what we do is we run survey scans as well as high resolution scans. The survey scans provide the elemental composition, and then the high resolution scans are used to elucidate the chemical state information. So the way that this works, just to give you a little bit of a background prep on XPS, is you put an X-ray in, that's the aluminum K alpha line that's coming in. The X-rays penetrate several microns, and you're looking at the electrons that escape. Now, electrons do escape from, probably a fairly deep, several hundred angstroms level, but only those that escape without any collisions, without any energy loss, are the ones that we're interested in. And those, to get 1 or maybe 1.5 mean free pass from the surface, is where you get your 10 nanometer resolution or your 100 angstrom resolution. So these are the survey spectra of 2 of the samples, the polypropylene and the polycarbonate. And here we're comparing, down here in red, the as received surface, which you can see a carbon peak and actually a little bit of an oxygen peak. And when you do the O2 plasma, you see the oxygen grows in significantly. When you do the fluorine plasma, you see you get a very large fluorine peak. And you see similar things here on the polycarbonate, where the oxygen increases a little bit here. And when you do the fluorine plasma, you again see a large fluorine presence. When we do the high resolution scan, here on the left, we have the polypropylene, which is essentially all just carbon-hydrogen bonds on the surface. Now, at the as received, we do see a little carbon-oxygen here bonding, and that's because adventitious carbon comes out of the air onto almost every sample, and you get a little bit of the CO and C double bond O just from the material that comes out of the air. After we apply the oxygen plasma, we can see that this carbon double bond oxygen has grown significantly. This peak actually shows the red here is the original spectrum, and then the blue area is the oxygen presence or the oxygen species that have been added. So carbon double singly bond and carbon doubly bound to oxygen get added here. You see a similar thing here in the polycarbonate, except polycarbonate starts out with another peak up here, and this is due to the aromatics here. They actually wind up with a peak out here. And when you do the oxygen plasma, you again see a large increase in the carbon singly bound to oxygen, and also some carbon doubly bound to oxygen gets added. And you can see the ratio here is almost 1-to-1 here on the polypropylene, whereas almost 2-to-1 here on the polycarbonate. So you're seeing a difference in the speciation enabled based on the polymer starting material. Now, when we do the fluorine plasmas here, you can see down here, you do get some added carbon oxygen bonding, but here this area here in the orange is sort of hard to see, but these are the carbon fluorine bound species, and that's a carbon singly bound with 1 fluorine, 2 fluorines, and 3 fluorines, and you can see that that occurs on both sample surfaces here. So to summarize the XPS, it shows that the surfaces exposed to the oxygen plasma, basically they get affected, and there's new species on the surface containing oxygen bound to the carbon in single and double bonds. For the fluorine, you only get single bonds, with the carbon, but some of the carbons pick up 1, 2, and 3 fluorines. We're unable to tell if these species go deeper into the sample. At the time that we did this, there's a sputtering technique you can use that basically removes material from the surface, and the capabilities we had at that time would basically just carburize our polymer, would just beat it up. We do now have some much gentler sputter methods. We may be doing that in the future to basically go and see if this fluorine and the oxygen has penetrated deeply into the material, or if it's just surface bound. But that's some work that we'll have to do in the future. And I want to introduce Janneke back again. Janneke is our expert on FTIR, and she ran these results, and I hope she'll come on in to explain it for us.
Hi, everybody. Thank you, Dan. So in addition to XPS, we also looked at these samples with 2 different techniques, FTIR and contact angle. So I'll start with FTIR. The way that FTIR works is instead of energizing the sample with X-rays, here we are using infrared light. And when the sample interacts with infrared light, you generate an absorption spectrum, and that spectrum is unique to all kinds of organic samples. So, let's see. So here I show an example of a common polymer, ABS acrylic, and what we see is a number of different bands, right? And each band corresponds to some kind of a bonding environment in the sample. So this polymer has double bonds, and they show up around 3,000, and then it has CH hydrocarbon bonds, and that shows up around 2,900. It also has a nitrile bond, so that's at 2,200, an ester, and so on. So you could see this is a fingerprint, and it really tells you about the kind of bonding environments present in the sample. And so it's really interesting to compare this to XPS and see what we saw on the surfaces. So the other thing I want to mention is there's a number of ways to do FTIR analysis. The typical way is in transmission, and you can, so you're just shining light through the sample. You can also come in contact with the sample using the attenuated total reflectance method. And so here you have a probe that actually touches the sample and is getting the signal from the top surface. There's also an even more surface sensitive technique that we recently acquired, and this is called grazing angle ATR. And this method actually gives you information about the top 10 to 100 nanometers. In addition, you can do FTIR using a microscope. And so some of these accessories are available with a microscope, such as transmission, reflection, and ATR. And in this particular case, we use the ATR, micro ATR technique to look at these surfaces. And so you can just imagine we would bring the surface up to our crystal and touch the top of the surface, and we probed a number of different locations to determine, whether the samples were homogeneous or heterogeneous. So now I'm going to show you the results. So for polycarbonate, we did not see any difference due to plasma treatment. at all. It seemed like it really had no effect. For the polyoxymethylene, the POM samples, we did start to see a slight difference. So, for example, in the O2 treated samples, we see the growth of a new peak around 3699, and this is possibly due to OH bonding, which makes sense. You could imagine a hydrophilic carbonyl-containing polymer, interacting with the O2 plasma and generating OH species. In addition, for the fluorine treated samples, we see a new peak around 1235, and this is typically where we see carbon fluorine bonding. So again, in contrast to polycarbonate, we actually do see some subtle changes. And then finally, for polypropylene, this is a sample where we saw fairly significant changes, especially due to the oxygen plasma. So if you look at the red curve, you see new functionalities around 1699, which is typically where we see organic acids. There's also a band at 1598, that's organic acid salts. And finally, we do see two peaks. We see a pretty strong peak at 1217. And we actually, interestingly, we see that both in the fluorinated and in the fluorine plasma and in the oxygen plasma. So we think that this could be due to CO or CF bonding. Unfortunately, for FTIR, those two vibrations usually appear in the same region, so it's kind of hard to tell exactly what is responsible for that change. So to summarize the FTIR results, for polycarbonate, we don't see any reaction to the plasma. For POM, we see additional hydroxide peak, and for the fluorinated, we see this peak at 1211, which we think could be due to carbon fluorine or potentially carbon oxygen bonding. For polypropylene, we see a more significant change. So for the oxygen plasma, we see the organic acid salt, and maybe CO-containing species. But for fluorine, we have that similar peak at 1217 that could be due to CO or CF. So when we think of these results in light of the XPS results, we do see some significant similarities, right? XPS definitely showed the presence of new carbon fluorine and carbon oxygen species, which is what we saw by FTIR as well. Now, the polycarbonate sample did show a change, but we didn't see any difference by FTIR. And we think that may be because of differences in mechanical properties between all these samples. Because polycarbonate is stiffer than polypropylene or POM, we think that it may be less reactive to the plasma. And so within the detection limit of FTIR, which is something like 5 to 28%, we did not see a change. So it's possible that a small change could have occurred. We didn't detect it. XPS is certainly more sensitive. The other thing that's important to note is the sampling depth, and we mentioned that in the beginning. XPS probes 10 nanometers, FTIR probes 1,000 nanometers. So perhaps just the very top of the surface has been transformed for polycarbonate, but that's not the case for the bulk of it. And so we're just picking up the signal from much deeper into the sample. So this is where that XPS sputtering technique would be really useful to see if the same chemistry is true throughout the sample. So the last test that we did was a contact angle test. So contact angle provides information about the wettability of a liquid on a solid. So how much does the liquid spread on the surface? So if it's a very hydrophilic surface, the water droplet is going to spread quite a bit, and you're going to have a very low contact angle. On the other hand, if it's a hydrophobic surface, the water droplet is going to beat up, and it's going to have a high contact angle. So it's a nice way to think about the hydrophobicity or hydrophilicity of the surface. And in this particular case, there's actually a number of ways to do the contact angle measurement. So the common way to do it is to simply put a droplet on a surface and take a picture of that and measure the angle. That's called the static test. In our case, we have dynamic contact angle measurements. And practically what that means is we take this little piece of plastic, we grip it, and then we slowly move it into the solution, into the water, and then move it back, right? This provides dynamic information, and it provides information about the entire surface that's wetted, not just a single droplet. So, and here's kind of a picture that shows you that, although you have to imagine the sample actually going in and being retracted. So when it immerses into the solution, that's when we measure the advancing angle. And that advancing angle is very similar to the static angle. It's you know, how easily does the water wet that surface. And then when we retract the sample back, that's the receding angle. So this is now characterizing the surface after it's already been wet. And here's what the data looks like. And so you can see here, this is polycarbonate data. And so we have the several measurements of the advancing here in the blue, and then the receding when it comes back up, and you can see the software gives us these numbers. So in this case, for polycarbonate as received, we found the contact angle to be about 86 for the advancing and 67 for the receding, with fairly good reproducibility. So the difference between these two, advancing and receding, is called the contact angle hysteresis. And what that tells you is how the surface transforms as a result of being coated in water, right? Because now it's a new surface. So first, let's look at the data for the control samples. So you can explain some of these contact angles thinking about the hydrophilicity or hydrophobicity of the polymer. So our lowest contact angle is for POM because it has a lot of these carbonyl functionalities, ether functionalities, so it's much more hydrophilic than, let's say, polypropylene, which is all carbon-hydrogen bonds, hydrophobic material, right, above 90 degrees. And then polycarbonate is a little bit higher than POM because it has these aromatic rings and some hydrocarbons, so it doesn't have as much polar functional groups. And so it's a little bit, it's kind of in between these two. And when we measured these samples, we achieved numbers that were fairly close to the literature values. So then the question is, what happens when we apply this plasma, right? So for the polycarbonate samples, kind of consistent with the FTIR results, we only saw subtle changes. So you could see that with the oxygen plasma treatment, we just went up a little bit. And with the fluorine plasma treatment, we went up a little bit further. But for the other two samples, we actually saw fairly significant effects due to plasma. So for POM and for polypropylene, we saw a decrease in the contact angle. So that means we're making a more hydrophilic surface when we, apply plasma, oxygen plasma to the surface. And conversely, for fluorine plasma, for all samples, we saw an increase in the contact angle. And again, for polycarbonate, it was a smaller increase. And polypropylene also did not see a significant increase. The really significant change was for POM, which was more than 46 degrees. And again, that's probably because this is a fairly hydrophilic polymer, and now we've put fluorine on top, and fluorine is hydrophobic. We all know Teflon, water doesn't stick to it. So it's the same principle. Now we've coated this POM with fluorinated material, and it's much more hydrophobic. Now, looking at the receiving contact angle results, first of all, we see that all the numbers go down significantly, right? And so that means that we have a contact angle hysteresis that's about 10, 20 degrees. So, and then for the treated samples, again, with polycarbonate, not a whole lot of changes. Interestingly, for polycarbonate and for polypropylene, the receding contact angle did go down, which is not what we expected necessarily. But for POM, it did go up, and just not as significantly. And in general, we did not see a lot of changes for the oxygen treated samples in terms of going from the control conditions. The receding angle stayed pretty much the same. And we did see significant changes for the polypropylene. It did seem to go down quite a bit due to the plasma treatment. Oh yeah, I just want to say one note. So altogether, we can see how XPS, FTIR, and these contact angle results all tell us a lot about, the properties of these materials, how they are changing, sort of the depth of information in these changes, and we are getting complementary information from these three techniques. So that can be really useful in making sense and trying to understand, how plasma can affect these polymers. It's clear that the three polymers are experiencing different things, and a lot of that is based on, the functional groups in these polymers. So now I'll give it back to Dan. Thank you.
Thank you very much, Janneke. That was very interesting there. One of the key points we're trying to make is that if we had just done one of these techniques, we wouldn't get all the information. And the reason we did these three techniques is they sort of made sense off the bat to be able to characterize particular things about the surfaces and be able to see the changes affected by the plasmas. There are additional analyses that we have planned, and we will probably eventually do, but we want to make you aware of them. One of the things that we thought might happen is a change in the surface roughness due to the plasma treatment. And we plan on either doing AFM, atomic force microscopy, or OP, or a stylus approach in order to measure the changes in the surface roughness before and after the effect of the plasma. Also, nanoindentation is another technique we have. This is different than the standard micro hardness tests, which go several microns deep, doing their basically indentation and measurement. The nano indentation goes much more shallow, and you can look at surface treatments or very thin films and look at the hardnesses there. And also time of flight SIMS, which is secondary ion mass spectroscopy, can also be used. It's got a very high surface sensitivity. It looks at the chemical components that come off of a surface when you sputter it. It gives you the chemical information, so you can take off, say, chemical compounds from the surface and be able to look at the breakdowns of those compounds in the mass spectroscopy, and you can get an idea of what the chemical as opposed to elemental materials are on a surface. And if we're open to suggestions, if there are other suggestions people have for ways to characterize these, we're happy to hear what you would have to give us as input. Just as a summary, the characterization of polymer surfaces after and before plasma treatment is useful to understand that what the heck has the treatment done? I mean, if you're trying to get something, say you're going to make your polymer case for your computer resistant to water, and you go do a surface treatment, well, you have to know what you've done in order to be able to improve that surface treatment going forward. XPS, FTIR, and contact angles all give us elemental chemical information and some information about the surface energy pre and post the treatment. With methods like this, you could build a design of experiment to optimize such treatments. And this is really the core case here, is if you're making a new treatment to alter your polymers, you want to know, did it work? Did it do the thing you want? And you also want to know what's actually happened on the surface, so you have an understanding of why it worked or why it didn't work, or what you should change in your process. There are links to a couple of our papers here. One of the papers, the second paper there, we're actually modifying in the very near future here. We're just tweaking it, but in a week or two, that should be all modified up. But this is where both of the current papers reside on our website. And you're welcome to go look at these things. And you know, so we have to do some advertising here. This is a business, right? So why would you choose EAG? One is that client confidentiality is core to our business. And that's part of why we went and got our own polymers, and we used our own plasma treatment source here. We didn't use any customer information here because we never share our customer information. We're the leaders in investigating science here. We have a large skill base and many, many tools. We have something like, I think it's 2,500 instruments at last count. We're a global leader for materials testing. We've been doing this for over 40 years. We also have ISO certifications, and essentially, give us a call and we can help solve your materials and engineering problems. And if we can't do the analysis ourselves, we'll work to find you a place that can. We are part of a larger Eurofins family of companies, and quite often our sister labs can do things that we don't, and we will work as hard as we can to try and solve your issue, even if EAG doesn't wind up doing the work.